Hello students, welcome back. We have one more subsection to go, and that's 3.4, Proof by Induction. Before starting, let's have a brief recap. In section 3, we went through a number of proof techniques. First, we went through proof by algebraic manipulation in 3.1, and then in 3.2, we went through the proof by logical implication. Those are direct proofs, and then there are some other direct proofs with some strange Latin names, but they're not really worthy of our class time, I think, so let's just move on. And then in 3.3, we went through the proof by contradiction, which is an example of an indirect proof. Now in 3.4, we have another indirect proof, proof by mathematical induction. How does it work? Here's a standard way. Let's look at this problem, for instance. We have a statement for integers. In this particular case, everything is positive integers. Sometimes we're going to need whole numbers. Sometimes we need some negative numbers as well, but in any case, we have to have an integer, or at least anything discrete. The structure is like this. We have to prove the base case, starting from 0 or 1 most typically, or something else. If the problem specifically gives you greater than or equal to 3, then you have to follow that. Or greater than or equal to -6, you just follow that. And then we assume the conclusion for n-1, which we call the inductive hypothesis, and then prove for the next n. Assume the conclusion for n-1, and then prove for n. Or equivalently, you can assume the conclusion for n and prove for n+1. Either way, it works out. Assume for 1 and prove for right next number. So assume for n and then the next number, or we want for n, so we start from the previous number. Either way. So in this case, we prove the base case. So it's starting from 1 clearly, so we don't have anything here in that case. N is equal to 1, which means, is this true? 1 is equal to 1 times 1 plus 1 over 2. Is this true? That's true. 1 equals to 2 over 2. Yeah, that's true. So base case is true. And then if you use this inductive hypothesis and the conclusion over and over again for n value 2, 3, 4, 5, 6, 7, and so on, we're going to get this. Plug in n equals to 2, so 2 minus 1 is 1. But for 1, it works. So it works for 2. And then plug in n equals to 3. 3 minus 1 is 2. But for 2, we just established it, so it works for 3. And then 4, and then 5, and then 6, and so on. It'll cover everything. Whether you do by n-1 to n, or n to n+1, either way. Which one do I prefer? I like to have n-1 to n. There's a bit of a reason for that. In any case, let's go through an example problem here. Base case, that's trivial. And then, let's assume inductive hypothesis. Assume this is true for n-1. So we have to get this one for n-1 version. In place of n here, I have to write n-1. In place n here, I have to have n-1. So this, as a matter of fact, is n-1 and then plus 1. You see, we have plus 1 there. So this whole thing is, as a matter of fact, n-1 over 2. And that's the inductive hypothesis. Alright, let's assume this is true, and let's prove n. So what's the inductive hypothesis? Add 1 through n-1, and that's this. It's highlighted in blue. And then add the same number to the left-hand side and right-hand side. And then we do some algebraic manipulation from this point on. Take the common denominator and then add up, factor out, simplify. What do you get? You get what you want. Precisely the conclusion you wanted. Compare that with the original problem. That completes the problem. And I like this better because I had to do some manipulation beforehand in the inductive hypothesis. That's basically a minimal difficulty. And that allows us to do this main body of the problem easier because you can drive toward the conclusion here. Now, if you take the second approach, it's a little bit different. Base case is the same, of course. And then we just copy down whatever it is. Inductive hypothesis is for n, so we just copy down. And then we're going to use that. And then add the same number, n plus 1, to both left-hand side and right-hand side. So far, so good. And then manipulate. Common denominator. And then factor and simplify. And what is this? Is that the same as this? Just n plus 1 version? Please check. Yes, indeed. So it works out. But that last checking may not be that easy, especially when you're still working on it. You see, in this problem, when you're doing the algebraic manipulation, you know the answer in advance. So you're driving toward this. So it's that much easier to manipulate. In this case, you're driving a little bit more blind because it's not this, it's n plus 1 version of that, so it's a little bit different. So somehow you'll have to work. It's not too bad because this problem is rather simple, but in more complicated problems, you don't have all the difficult steps in a single step right here. And one step that is super hard and one step trivial versus one step minimally difficult and then one step not super hard but okay. Which is better? One super hard and one trivial versus one minimally difficult but one hard but not super hard. That's why I prefer the first method. Assume for n minus 1 and prove for n rather than the other way around. Let's see, do we have time for another? Well, let's review it briefly. The base case, we have to start from 1, of course. So throw all those away. 1 squared is equal to, plug in 1, and what do you get? It'll check out okay. 1 squared is equal to 1 plus 2 plus 1 times 2 times 3 over 6. Yeah, it works. Please check. And then this one in n minus 1 version, replace n minus 1 in place of n here, here, and there, and simplify. And that's my inductive hypothesis. You see, this one is not that trivial because I have to replace n by n minus 1 and do some manipulation and simplification, but it's minimally hard. And then use that inductive hypothesis and then add the same thing to both left-hand side and right-hand side, and then take the common denominator, simplify, factor. In the end, am I getting exactly what I wanted to begin with? Not too bad. You know the answer in advance, so you can drive your manipulation that way. Now, if you take the second approach, inductive hypothesis just trivial, just copy down, nothing. But this algebraic manipulation, where am I going? That can be a bit more challenging. And then here's another one here, and that's also left as an exercise for you. Okay, so much for standard induction. Base case, assume for one number, and then prove for the next number. Another way to use the induction is to use strong induction. Assume for the base case. So I use B for base case, and base case is 0 or 1 most typically, but sometimes something else. The problem will explicitly tell you. Next, assume the conclusion for all integer greater than or equal to the base case and less than n. Not just one integer and going for the next, but you have to use all integers here and then prove for n. So that's a bit harder. Let's see, ready for an example problem? Okay, stop the playback and try this. Okay, that's true for all integers. Does it work with mathematical induction? But then again, it says all integers, but look at this. It's symmetric, n and negative n. So if I take negative n, that's the same. So if I just prove that for all whole numbers, then we are true, and we don't really need to prove for all whole numbers. If n is 0, then x to the 0 power, that's 1. X to the 0 power again, so that's always integers, so no problem there. So as a matter of fact, you're proving only for positive integers. You see the base case? When n equals to 0, it's trivially true. X to the 0 power is 1. X to the negative 0 power is also 1. Negative 0 is 0. So that's an integer. When n equals to 1, yeah, the problem says that's a condition, so yes, that's an integer. Now assume the conclusion is true for all integers greater than or equal to 1 and less than n. In that case, the conclusion is true. So as a matter of fact, I forgot this. Greater than or equal to 1, less than n, then x to the k power plus x to the negative k power is integer. Okay, how does it help getting the conclusion x to the n power plus x to the negative n power? Let's use an ingenious idea. We're going to multiply the special case x to the n minus first power plus x to the negative of that times x to the first power plus x to the negative first power. This is an integer because of the inductive hypothesis, and that's an integer by the original hypothesis, and let's work out. Fold it out, and what do you get? Stop the playback and do it. If you do it right, you're going to get this foiling. First, outside, inside, last, so that we have x to the n power plus x to the negative n power, something you wanted, and then x to the n minus 2 power plus negative of that. But that's an integer because of the inductive hypothesis. You see, that's an integer, and that too is an integer. So the quantity we want is integer times integer minus integer. So yes, x to the n power plus x to the negative n power is an integer. And that's true for all positive integers, but because of the symmetry, it's true for negative integers as well. And then the trivial case, n equal to 0, we went through that already. So the conclusion is, it's true for all integers. So strong induction problems can be rough. And if you think this was hard, here's even bigger challenge. Okay, I'll leave you with this problem. I do have a solution here. Set up the full solution. Okay, let me show you up to this point. Plug in n equals to 0, 0 squared, so it works out. Plug in n equals to 1, 1 squared, it works out. And set up the inductive hypothesis. And then here's a big hint. Consider n is even and n is odd separately in this order. Good luck. This is super hard.